All right, well, I trust you did well on your special triangles quiz. Students in here, for the most part, did well. Some little things we needed to address a moment ago before we started recording. If you would take out your textbooks, turn to page 214. And on page 214, you'll see Theorem 65. We've already addressed that. We practiced it extensively yesterday. A fact that is true about similar polygons, and specifically something that's true about the sum of the sides, or sums of the sides of a couple of similar polygons. First of all, Genesis, what do we call the sum of the sides of a polygon? Perimeter. And we said that if two polygons are similar, there's something special about their perimeters, Quentin.
They'll be proportional.
They'll be proportional to what? They'll be proportional to the sides, exactly. So that the ratio of the perimeters would equal the ratio of the sides, or in other words, Audrey, the ratio of similitude. So I gave you a proportion to know in your class notes, and Chris, what was that proportion we worked on extensively in our last lesson?
P is to P prime as S is to S prime. S is to S prime?
Good. P is to P prime as S is to S prime, or in words class, say it with me, perimeter is to perimeter as side is to side. And again, the only thing we had trouble with yesterday every now and then was making sure we saw, was it first polygon or second polygon? Remember that? So being careful with that. I feel like yesterday we did plenty of practice, so we're going to move on. I want you to look at Theorem 66. We'll discuss it very briefly, not taking time to prove it, but an interesting theorem and something we will use in construction actually later on. Go ahead and read Theorem 66 for us if you would, Jamie. Page 214 is where we should be.
Okay. If two polygons are similar, then they may be composed into the same number of triangles similar each to each and similarly placed.
So you have similar polygons. They can be decomposed or broken down into the same number of triangles, similar each to each, and similarly placed. Look across the page if you would. There's a picture of this. You've got the larger pentagon, A, B, C, D, E, and the smaller pentagon, A prime, B prime, C prime, D prime, E prime. And the idea here is you could, from a single vertex, E and E prime, draw your diagonals. Well, first of all, if the polygons are similar, they must have the same number of sides. We've already established that. If they have the same number of sides, then they will have the same number of diagonals drawable from a vertex. We've already established that. If that's true, then every diagonal that's drawn, as you see there, will form a triangle, or rather, triangles. And so in the case here, if there's 5 sides, you will get the same number of triangles, n minus 2, which is something we'd already pointed out, but the triangles will be similar to each other. How would we prove, for instance, looking at the picture there on page 215, looking at that top picture with the dotted auxiliary lines, that let's say triangle Abe, seems like an honest enough triangle, would be similar to A prime, B prime, E prime. Thoughts, Kendall? It's true the perimeters are going to be proportional, but Chris?
Similar prove similar.
Yeah, how would I get those two triangles, ABE and A prime, B prime, E prime similar?
AA?
Well, for angle, you need more than just one set of angles. And obviously, as we look at it, if the polygons are given similar, then I know A and A prime have to be equal, correct? Because corresponding angles of similar polygons are equal. It's what makes them similar. But I don't know about the angles at E and B, because, or E prime and B prime, because those are angles we formed. They weren't given to us. Other thoughts? How would I get the triangles similar? Because if the polygons are similar, the sides are proportional, so we know that AB is to A prime, B prime, as AE is to A prime, E prime. So not by angle, but by side, angle, side, those two lower right triangles have to be similar. Once established similar, all their angles would have to be equal. We would do the same thing for CDE and C prime, D prime, E prime. Again, side angle, side, we could get those triangles similar. Once similar, we know corresponding sides are proportional. We could use that. We could actually use side, side, side to get the middle inset triangles. And the same would be true for really any similar polygons we would break down. Just an interesting fact for now, that if polygons are similar, they could be broken into the same number of triangles, similarly placed. Again, later we'll actually do a construction based on this. Look at Theorem 67. It's the converse statement. Chris, read it for us.
Two polygons are composed of the same number of triangles, similar each to each, and similarly placed in their similar.
Yes, this says, well, what if you put together the similar triangles similarly placed, and then you would be able to form polygons that are similar? Well, again, if the triangles are similar, then all of their angles have to be equal and their sides have to be proportional. Once you know that, you can extrapolate out that the sides of the polygons would have to be proportional in kind. You would also be able to, maybe through the addition axiom, extrapolate the angles are equal at all the vertices. If all the angles are equal, all the sides are equal, polygons have to be similar. So again, the proofs would be rather lengthy, though not really hard, I don't think. But for sake of time, we'll bypass that. I want you to turn over now to page 216. Just kind of tuck that thought away. You'll be copying those in your notebook for homework later. I want to do a proof with you in the, 15 minutes that we have left. Page 216, number 1. Page 216, number 1, and Genesis, if you'll go ahead and read that problem for us.
P is any point in arc A, PB, and C is the midpoint of arc ACB. The chord AB cuts chord CP at E, proves that triangle APC is similar to triangle EAC.
Jamie, read that for us.
P is a point in arc APB, and C is the midpoint of arc AC. If chord AB cuts chord CP at E, prove that triangle APC is similar to triangle EAC.
Ethan, read that for us.
P is any point in arc APB, and C is the midpoint of arc ACB. If chord AB cuts chord CP at E, prove that triangle APC is similar to triangle EAC.
We've read it 3 times. At your seats, draw the picture. That's what you would want to do on homework proofs. Read it a few times, make sure you understand what you're drawing. How many knew to start with a circle? The word circle doesn't appear, but what words do? Arc and chord. So you know you've got to have a circle. All right, several people are finishing up the picture. All right, for sake of time, let's see how you were doing. Obviously, it doesn't tell us the name of our circle, and really, truly, the center point isn't particularly important, but just for old time's sake, I'll name it Circle O. You didn't necessarily even have to name the circle. You did have to name an arc, and you needed to name it AB. So you need to pick any random point on the circle, doesn't really matter where, maybe something random like this, and you need to pick another random point anywhere on the circle, preferably not directly across to imply a diameter, but maybe something like this, and call it B. You then should have picked any random point on the arc and called it P. Any point. Closer to A, closer to B. Probably shouldn't pick the midpoint though, right? But any other point would work, and I'll just pick a point here. How many did create some arc on the circle, called it AB, and picked a random point, not the midpoint, called it P? Then there's one other really important point we need to mark, and that was the midpoint of the other arc AB. This is arc APB, but of course I could go the other way around the circle, and I could call this arc ACB, where this time specifically C is the midpoint of the arc. How many labeled C as the midpoint of the other arc AB? And you could have had P in the major arc and C in the minor arc, that's fine, but you had P in one arc AB, C is the midpoint of the other arc AB. How many recognized that? We also then had to make a chord AB. So once we determined where our arc's endpoints were, we draw the chord AB, and we also have the chord CP. How many drew the chords joining those points as instructed? and then named the point of intersection E? How many also had the intersection point labeled E? How many then had a perfect picture? Okay, a few of you did. Good. Those who didn't, does it make sense now? Go and fix your picture if you didn't already have it. Let's go ahead and get down our given, and we are given circle O, as I'm going to call it, with P, any point in arc APB, and C, the midpoint of arc ACB. You realize essentially all I'm doing is restating the problem. I can also state, just as it says in the problem, that AB intersects CP at E. Is it necessary entirely to state that? I don't know that it is. We could probably get by without even saying that the chords intersect each other, since it's pretty obvious from the picture they do, but it doesn't hurt to get it in there, especially if you're going to take the argument we can't trust our eyes. How do I know they intersect? Well, we couldn't have a point E if they didn't, so they must intersect, but I digress. All right, what are we trying to prove here? Genesis?
Triangle APC is similar to triangle EAC.
APC, the triangle, is similar to
Triangle
EAC. All right, I don't see any triangles, period. So to make triangle APC exist, what would I have to do, Chris?
Draw the auxiliary lines.
Which ones?
AP and CDA.
Okay, I'm going to have to draw an AP, and I'm going to have to draw CA. All right, that gets the triangle APC. And EAC, okay, that's actually drawn now already. So that's interesting. We're trying to prove that this triangle is similar to this piece of itself. Interesting. Go and get down your two columns, statements, reasons. Circle O with P, any point in arc APB, and C, the midpoint of arc ACB, AB and CP intersect at E. So there's one triangle. There's another triangle. All right. Well, before we get too far, Chris had us draw some lines. We should go ahead and get that down. Number 2, Chris.
Draw AP and AAC.
Reason?
2 points determine a straight line.
And there is an important clang we really ought to go ahead and take care of. Again, we're not always blessed with clang. We definitely got some clang going on here, Audrey. Yeah, this whole midpoint thing. So what could we state because of a midpoint? There we go, AC and BC, the arcs are equal, good. Arc AC equals arc BC, reason? All right, and I think that's about it as far as clang, and of course we took care of those auxiliary lines. I want triangles similar. How does that usually happen, Kendall? Usually angle, okay, so it's kind of hard with these triangles because again I'm looking at this big one and this piece of one. Kendall, thoughts? Yeah, we could unoverlap those if were so inclined. I could kind of draw what appears to be kind of like ACP here. Of course, E is kind of like that. And then I could draw EAC. Kind of looks like that. So that just kind of helps me to see the two triangles separately. Of course, we can still reference them on the picture. But, oh, you said we want to use angle. Thoughts?
Angle C.
Yeah, this angle C is the same in both triangles. So, yeah, number 4, that's the only angle at C. So I'm going to say angle C equals angle C by identity. And very often we've been blessed with shared angles. That takes care of one of the angles. So really, any other angle, and I'd be good to go. Just a thought, without even really doing too much more thought, maybe even just looking this way. Ethan, what other angles might we try to get equal?
Angle A would work because of it being 2.
Ah, good point. It would not work to say A and A are equal because one A is this piece, the other A is this whole thing, and the whole is never equal to one of its parts. It's always greater than any of its parts. So if A won't equal A, then A might equal, let's take this A, for instance, would have to equal, if it doesn't equal A, it would have to equal, there's only so many angles, right? This angle A, you said, cannot equal this angle A. So therefore, if they're going to be similar, this angle A would have to equal the angle at E. Or I could get the little angle at A equal to the angle at P. It's one of those two. Either I'm going to call this angle 1, I'm going to call this angle 2. Either angle 2 equals angle P, or we could get the whole angle A, I'm going to call these 3 and 4, or the whole angle A could equal angle 4. Do we all see that if I can get one of those two statements to be true, I'm in business? All right? Thoughts then?
Angle P
Jamie?
would equal the arc AC.
I'm sorry?
Angle P equals the arc AC.
Angle P equals arc AC. So number 5.
Oh, is it half of arc AC?
Oh, that's true. Angle P equals half. And there is only one angle at P. Yes, equals half of arc AC. Okay, because?
An inscribed angle is equal to half its arc.
So your thought being, Jamie, let's just take this first one and see if we can do something with it. What do I know about angle P? Well, it's an inscribed angle. What do we know about an inscribed angle? It equals half its arc. So let's kind of ride with that. That's what we know about angle P. What about angle 2, Quentin?
Angle 2 equals half arc BC.
Okay, angle 2 equals half of arc BC. How do we know that? Oh, same reasons. This is actually still part of number 5 then. Thoughts now, Ethan?
Angle P equals angle 2.
Oh, I'm sorry, I said angle B equals half angle arc BC. I'm sorry, angle 2 is what Quentin had just said. And so now you said number 6 that means?
Angle P equals angle 2. Substitution. Well, they equal the same.
They don't
halves
equal the
equals
same
13.
thing. They equal halves of equals. There we go. Now, if we were to substitute once and then substitute again, we could do that. But this is quicker to say halves of equals are equal. Very good. Yeah, angle P is half of AC, 2 is half of BC, because they're both inscribed angles, and AC and BC are equals. These are both halves of equals. They are equal to each other. And, well, there's my P and 2 equal. C and C equal. There's my angle. So in 7 steps class, we have our similar triangles. Triangle APC is similar to EAC by angle. Had we chosen to go with the A and the 4, it would have been a lot more dicey. You would have had to say, first of all, well, A is equal to 1 and 2 added, or perhaps A, the whole thing, is equal to PBC, which is PB and BC added together. the angle 4 would equal half of PB and BC added together. 4 formed inside the circle is half of AC and PB added together. But AC still equals BC, so you could substitute. And then, of course, 4 and A could have been equal. A lot easier to go with the P and the 2, so it's a good choice by Jamie there. Questions on this? All right, your homework for this evening, first of all, is to copy Theorems 66 and 67 into your notebooks. Copy Theorems 66 and 67 into your notebooks. Again, not doing the proofs, just getting them copied down, and know that fact, that you could break two similar polygons down into the same number of triangles. They'd all be similar to each other, and they'd all be similarly placed. Well, similar each to each, not all similar to each other, similar in pairs. Make sure you know that. And then also study pages 210 to 215. Study pages 210 to 215. We're going to take another quiz tomorrow. It will include special triangles, but that won't be the main thrust. It'll be all the stuff on pages 210 to 215. So a good review of what we've covered since the last test. Okay, so all the material for the quarter pretty much summarized on this quiz in short form. We are looking at a test in a little over a week. I'll give you some more specifics as we get closer, but test is still about a week away or so. All right, you are dismissed. Have a wonderful rest of your day.